what's the topic you pick up? 13? Okay. So for the groups, three groups, please write down.
放钱了吗？放钱。不要回答不出来的时候打断他。记得不要回答不出来的问题。如果回答不出来的，不要让这个题目这个。那就是你讲完你的想法之后，你就把它传给
The recorder, you can start when you're ready. When you're ready, you can start. Not yet? Okay. Then take your time. You can start anytime when you get ready.
I'm the reporter from Variable 2, and my name is Yang Mianjun. Today, we are talking about the problem is the problem at spaghetti accelerator. And here's the problem statement. When a piece of spaghetti is pushed into a bent tube, small barrels of spaghetti may be ejected from the other end of the tube at a surprisingly high speed. Investigate this phenomenon. My main focus is the geometric structure of the tube and the energy causing of the acceleration and the resulting parameter related to the velocity and phenomena. And eject the spaghetti and the tube of the wall cause the deformation and diverse structures and injects. You can see on the videos. And inject the spaghetti into the tube at varying velocity while ensuring the tube shape remains constant. And here's the result. Inject velocity is always greater than inserted velocity. And as you can see, the change in the velocity is almost the same. The theory. And this one describes the spaghetti's deflection, and we plug into the equation. It will become this, and we will calculate later. And this one about blocking, and this force is the tube to the spaghetti, and this force is the force is by hand, and we both to push the up to side of it, and it will cause the force maximum of the critical force vertical load on the column. So means the point is right here. And moment curvature. Before the material cracks, moment and curvature have a linear relation. Means right here. Linear relation. And this equation just means it's linear. The spaghetti cracks at the MC. This crack at this point. At this point, the curvature reaches its maximum value, and the stored energy transfers the kinetic energy to accelerate the spaghetti. The x-axis means the phi CRY, and it means the curvature, and the y-axis is about the moment. And this one is in the linear elasticity, and this one is the strength. And we put in a result is the maximum allowable strength. And this picture just talk about the curvature of it. And here's the meaning of the equation. And strength and moment. Right here as the result, you can see right here and right here. And the meaning is your teammate's moment, it will cause the maximum magnitude of stress and will cause the minimum radius of curvature. The U means right here is the definition of U, and we calculate that, and this equation we will calculate later. And all in front of it is constants. And you can see a picture over there. The x means the small distance that refers to the radius of the curvature. And injected velocity is always greater than inserted velocity. If the internal velocity is 0, the change in velocity is the same. Measurement, Young's modulus. And this one means the deflection, and this one means the moment of inertia of the circular cross section. And we plug into that, and the result in question is this. And this one means both the sides are fixed, and we hand in a 15 grams weight over there, and it will cause a deflection. And the deflection the fraction we case is 46 millimeter, and we calculate it, and we will know the Young's modulus is about 1.687 GPa. Experiment 1, the fracture conditions. If the shape of the tube is the same, the strain generated in spaghetti should be the same. The position where the greatest strain generated is also the same. So the result is the ejected length of the spaghetti should be the same. There's the experiment list. Depending variable, the diameter of the tube, and depending variable is the eject length and the maximum curvature. And experiment setup. Spaghetti, the diameter is about 1.6 millimeter, and the Young's model we just calculate. And the tube is 3 types. The diameter is 3 and 5 and 7 millimeter, and the angle of the same is about 140 degrees. The ejected length. Insert spaghetti into a tube, and we place the spaghetti at rest at the turning point, then push it into the insert. The internal velocity is 0, and measure the then inject spaghetti. The maximum curvature, and we inject the spaghetti and capture the fracture moment and analyze with the image J, which is about like a shaker, and to find a point of curvature. And 4 is find the maximum curvature and calculate distance from the end point of the point in the minimum radius of the curvature. Right here is the D. So here's the data over here. And the distance and the diameter of the tube. And this graph is talk about the relation between the tube diameter and injected length. And the x-axis is talk about the tube diameter, and the y-axis talk about the length. And you can see the orange D and the blue one injected length is very close. And experiment discussion. Based on the moment curvature, the spaghetti fractures the points of the maximum curvature. So the extract distance and the distance between the end point and the point of maximum curvature should be the same. That's right. It means the D should be the same. Experiment 2, inject velocity. But experiment least independent variable, the determinant of the tube, and determinant variable inject velocity. And the experimental setup, spaghetti determinant is 1.6 millimeter, and the Young's model is just the same, and the tube just the same over last experience. And the experiment procedure, insert the spaghetti into a tube, place the spaghetti at rest and the turning point, then push it into an insert. The internal velocity is 0, and measure the inject velocity by shaker. And here's the data over here. And this graph is talk about the relation between tube and diameter and velocity. And you can see the green, and you can see the 9 is 0, so we'll talk about later. And because the internal velocity is 0, so we don't calculate this n1 over here. So the velocity equation is right here. And the strain energy, and we just according to the distribution of the curvature, the strain energy is almost the same. And mass of the barrels. Based on the first experiment 1, the length of barrels is 0 millimeters, small to the 5 millimeters, and 7 millimeters. So the result is the n is equals to the length of the barrels. And the discussion, we are calculating about the velocity, and the U means the strain energy almost the same, and so the result is the V is 3 millimeter is bigger than 5 millimeters and bigger than 7 millimeters. So let's let's discussion why 9mm didn't crash it. Because each millimeter has the critical curvature because the determinant is not big enough, so the spaghetti didn't fracture. And the graph over here is talk about the point curvature, and the x-axis is talk about distance, and y-axis is talk about point curvature. And here's the reference. I searched for it, and thank you for listening. You mean the problem statement?
Yes. Send that down, please.
Okay.
Yes, down. And how do you measure the B0 in this case? And
We use checker to make sure that B is the zero. Because in the video we use the checker to make sure the zero point over there, and the next moment it will push it down. It will push it down.
projects out.
Yes.
And can you go to page 12? And so you said that the curvature reaches its maximum value at this point, right?
Yes.
So you said that this is curvature. This is the axis of curvature.
Yes.
Let's say it. So the curvature keeps on getting larger after it ejected. So why is it the maximum value?
Because the spaghetti is quite cracked in here, so
So we consider the maximum value before the spaghetti breaks, right?
right before.
Okay. So can you turn to page 15? So the x symbolizes the here or here.
Symbolize here to here.
What is the x?
The x.
Yes.
The x is the most distant because we just spread it into a small distance, and I want to talk about is this distance.
Okay. critical provision. curvature是个三 C。我就写了。然后本期没有发现差异比较大。请多慢点，别理解。 I'm the opponent from Banana. We're talking about the question number 13, spaghetti accelerator. The problem statement is as above, and the key points I want to, in this case, is the geometry structure of a tube, which is spaghetti in this case. The energy that causes the acceleration to occur, which means that the spaghetti ejects out of a tube. And we also discuss about the relevant parameters related to velocity and probably some relative expressions about that. And the overall view of the report that the report has presented, in theory, they use the Young's modulus and the bending bucking transformation and force to develop an easy and simple and easy to follow theory. And the potential, they also mentioned about the potential strain energy that spaghetti has, and the moment curvature, which as an extent will make a spaghetti eject out. And they talked about linear elasticity and strain, which in the results they said that there's a maximum affordable force of a spaghetti. And in its experiment, they use a tube shape and with a certain angle and measure the curvature and the V should be quite relative. And they insert spaghetti with V0 equals 0 to prevent the extra energy applied onto the spaghetti. And they use trackers to analyze the data. And in conclusion, they said that the diameter of a tube affects the velocity, and inserting the spaghetti into the tube and can ensure the initial velocity equals 0. And as is stated above. Next one. And here are advantages and suggestions to a reporter. And we can say that they have a comprehensive theory explanation of this phenomenon, and it's easy to follow, and they have pair chat and experiment process. And some suggestions about that is the pronunciation of several important words are confusing, and you have to do some clarification for them. And as I stated before, we aim to explain this phenomenon more in a quantitative way rather than quantitative. So it's better to insert some maybe some relational expression into this to better explain this formula, and better explain this phenomenon. Okay. And some points I want to discuss in the discussion session is that the graph on page 9 is not unfair. There's just some things I want to clarify. And some energy loss and the critical curvature that is stated, and the fatigue of a spaghetti when inserting into a tube. And about the experiments, I want to investigate the small pieces flying up and like the debris that is stated, and that what impact angle could have on page 29. Okay, so let's invite the reporter to a stage. Also, I want to start with the graph on page 9. Can you turn to page 9? As the experimental video shows, your spaghetti one side of the spaghetti is on here, but now it's like there's only one point in contact with the tube that's lower in curvature. So can you explain that?
I say that because we push, and this force we push it by hand. So this is this one we push by hand, and it will cause the tube, right? And right here is the tube, the tube push force over here.
So you're stating that here's the force we apply by hands, and here's the force applied by a tube, right?
Yes, because the broccoli is the spaghetti, and you push the force and both sides.
Oh, so you simulate the both hands movement by letting the tube push on one side and the hand on another, right? Can you turn to the video? That's not the point I was trying to say, because you can see that this is the maximum curvature that the tube can have here, right? Here.
No, it's at this point.
Yes, the spaghetti is in contact with heat, with a curvature here, in the inner curvature here. But in your theoretical model, we can see that the spaghetti is in contact with the smallest curvature here. Can you turn back to it? Rather in contact with here, then you let the spaghetti bending this way, which can I use a factor? I was talking about this point. The spaghetti should be here, but in your state, it should be in contact with this. So it should be like it should contact the both two sides of the tube, and
you push the spaghetti right here by hand, right?
yes.
And the spaghetti will become it will touch the tube, so it won't get like this.
So do you agree that this point is in contact with here, or can you visualize which side of the spaghetti is it touching on the tube?
Which side?
Which point is in contact with the end of the spaghetti?
Spaghetti here this point it touched the tube. At the point is it touched the tube.
Okay. But in the experiment video, the spaghetti isn't like the one you shown here. The spaghetti should be in contact. The longer end should be in contact with the outer layer, while the
Let me draw the picture.
okay.
It will become like this. I don't know what you mean, but I mean this will touch. Here will touch, and it will become the external curvature.
Oh, so you said that it should be in contact with the outer layer rather than the inner layer.
You mean the spaghetti?
Yes, for the spaghetti to have the smallest impact on the force, because you said that the spaghetti will break if too much curvature is added, right? Yes, is that true? So the curvature here can be approximated using a circle. So this circle is relatively small, right?
Right.
So,
Calculate this one.
So this is the theoretical model that you're suggesting. So now for my theoretical model, I'll make the spaghetti in contact here and make it contact on the other side. Well, the curvature at here be larger than the curvature at here.
And at my report, I don't calculate this one. I just calculate this one, and it will relation to our experience.
And so I'm not talking about the correlation between your experiment and your theory. I'm just stating that by your theory, if you draw your picture, and stated that the spaghetti is in contact with the outer layer of the tube, that it might have a bigger curvature, and the critical curvature might be unclear or even wrong if you use this as your theoretical calculation basis.
And here we only focus on that.
Okay, so what about the next question? I want to talk about the energy loss that when you are using your. Can you turn to the page where we have 42, page 42. So what do we get? So can you explain to me what do we get from this chart?
The relation between the tube diameter and the velocity. And means the tube gets bigger and the velocity will decrease.
Okay,
And
so by this experiment, we can state that. Can you agree with me that the curvature of a spaghetti tends to be the smallest if it can, right?
But I don't talk about this point. I talk about this point.
They talk about the outer point of the tube.
Yes.
Okay. No, I'm not focusing on that question. I'm just asking you if the spaghetti tends to be less complex and more relaxed state. Do you agree?
One more time.
Do you think that the spaghetti tends to be flat line rather than bending.
Yes, yes.
Okay, so can you turn to page 30? I want to talk about the question of fatigue. So as you stated that when doing your experiment, you inserted the spaghetti into the tube while maintaining the velocity at 0. And when you apply a little bit of force onto the other end of the spaghetti will break and fly off. Is that right?
Now, I don't. The velocity is 0. Before the velocity is 0, and the last moment it will push out. So I don't push another force to it.
So why would it break on its own?
Because the velocity 0 is. Let me draw for you. I push it on this, and it will touch this one, and the velocity is 0, and another second it will come out. So I don't push another extra force, and I mean right here is the velocity 0, and
It's a critical point, right? It's when any little force is applied to it, it will break. Even on its own, it will break, right? Yes. So I was wondering. I will finish this correctly. It should be contact. Yes. Right. So when it breaks, no force is applied. So you are assuming that the spaghetti will break on its own even when no force is applied.
No, I missed right here. This point is, I push the force of this, and I use the tracker to find the point of the velocity is 0, and the next moment it will come out. So I don't push the force. I push the force before I search the velocity is 0.
Yes. So let me rephrase it. So you put the spaghetti here, and that you use tracker to measure that its velocity is 0 at this moment, and that it will break off, and you measure the beat, and no force is applied in this state during this time. Is it?
No force?
No force. No force is applied when the tracker is tracking this movement. Is that right?
You mean the
No external force. No external force is applied. Is that right?
Because before I push the force into the spaghetti, so.
Okay. Okay. So let's go to the next question. Can you jump to page 46? Let's ignore that for a second. And so you're talking about the critical curvature where the spaghetti breaks, right? Critical curvature where the spaghetti breaks on its own, okay? Which means that the spaghetti is in a very bended state, and any applied force will break the spaghetti into pieces. Is that right?
Right.
So you suggested this. So you suggested this theory. So can you tell us what is the critical curvature in the experiment? Because you said that the 9 millimeters cube wouldn't break on its own. So what is the critical curvature of this experiment? Or what is the critical length of this tube? How wide has it has to be for it to not break?
Very nice discussion.
Okay, thank you.
Time's up. So please conclude for 1 minute.
Okay, so in the discussion we talked about the graph on the page 9, and the graph. I think there's flaws in this graph because I don't think that the reporter's flaws and my flaws on the spaghetti is. I think the flaws were different, and I think that needs to be clarified because they are using this graph to do the calculations and doing the experiment. So I think that we should all agree on the same model for it to continue. And so we'll talk about the energy loss of this motion, of this. We didn't talk about that. Also, next one is a critical curvature of this problem. So I asked about how wide the tube has to be for the spaghetti to not break, or how bent it is for it to break on its own. And there's a weird thing that they mentioned in their experiment is that the spaghetti will break on its own even when no force is applied, and I think that's pretty weird. Okay, thank you.
Thank you very much. So for the reviewer, you can ask questions for the two opponents.
And the question for both reporter and opponent, I want to ask, what factors cause the high speed in problem statement? What factor cause the high speed?
Cause the high speed?
Yes.
The strain energy. Spaghetti strain energy.
About opponent?
I agree with that because the bending extent of the spaghetti has the potential energy stored in the spaghetti. So when it releases, a large portion of it will be carried out by the kinetic energy.
And next question, what caused the spaghetti to break?
What caused the spaghetti to break?
Yes.
Because each material has the critical curvature, so if it touch the point curvature, it will break.
Okay, thank you. And about opponent?
I think it's a critical curvature for it to break because when it reaches a critical curvature, as the reporter stated, the spaghetti should break on its own even when no force is applied.
Okay, thank you. And do you think the spaghetti will rotate during the ejection? Do you think the spaghetti will rotate during the ejection? And how about opponent?
I think that spaghetti that flying, the debris that's flying out should have different kinds of motion altogether, and that altogether considered should be the kinetic energy of the spaghetti debris that it contains.
Okay. And
if the angle is vertical, so I think it will. Never mind. I think that it will. I will rotate.
okay. And next question, which force change the ejection direction of the spaghetti? Yes. And how about opponent?
Can you read your question again?
And which force change the ejection direction of the spaghetti?
As you stated before, as you have questioned before, there's movement on the debris, and that is unpredictable to have predicted where it will eject. But I think that it should be unpredictable because there's different kinds of.
Okay, thank you. And next question, will it always? Okay.
The plane contract the tube.
The ejection direction will change.
Yes.
And why?
The planes contract the tube.
It's time. Sorry, time's up. Sorry.
Yes,
Hello everyone, I'm Review Wang Zhiru from Team Photon, and today I'm going to review problem number 13, spaghetti accelerator. And there's problem statement, and my main focus is the main reason of the high speed and what factors will affect the high speed. And there's a review of the report. In theoretical model, she talk about beam theory, stress and strain, moment curvature, gas modulus, energy conversion. And I think she explained the theory clearly, but she didn't consider about the contact area and lack of considering the energy loss. And in experiment and setup, she changed the tube diameter and outlet. She changed the outlet diameter and insert and curvature, and I think she considered the coefficient of the friction of the tube, but she didn't explain how to get the thrust and ignored the rotation of the spaghetti and didn't mention the changing range about the angular velocity. And in data analysis, she talked about the maximum curvature and insertion length and angular velocity. I think she considered the coefficient of friction of the tube and control the inserting force. But I think she didn't explain the effect of rotation and the contact area, and didn't measure the mass and length of error bar. And there's review of the position. In short question, she talked about the moment curvature change and clear term meaning about the beam theory. And I think she mentioned whether the critical value exists, and I think he lack of discussion of data trend and lack of discussion about setup, and didn't mention the energy conversion. And in discussion time, she discussed about the reason cause of spaghetti to break and the critical value about the length. I think he connect with his short question and asked about why the spaghetti will break. But I think he lack of discussion about the reason cause of high speed. And he discussion one, the opponent X which force on the center of the spaghetti make the spaghetti break, and he think it is the force by the tube, and the reporters think the force about the two sides of spaghetti make the spaghetti to break. And I think and I agree with the opponent. And he discussion two, the opponent X which curvature make the spaghetti eject, and she think it is the curvature of tube, and the reporter think it is the curvature of the spaghetti, and I think the curvature of the spaghetti is the main reason because it will cause the elastic potential energy that transforms into the kinetic energy. And on question one, I asked what factors cause the high speed, and I think it is because the elastic potential energy will transform kinetic energy, and the mass of the spaghetti is pretty small, so it will cause a high speed. And the reporters thinks the spaghetti strength energy, and the opponent agree with me. And our question two, I asked what caused the spaghetti to break, and I think it is the stress in the center of the spaghetti, and it will break at the point of maximum stress. And the reporters thinks the critical curvature about the spaghetti, and the opponent thinks the critical curvature about the tube. And about meeting point, I think the opponent didn't, in discussion time, talk about the reason that caused the high speed, because in problem statement, I think we should focus on the high speed, and I think the mass is pretty small, and the elastic potential energy transform the kinetic energy is most important. Thank you.
And here's the concluding remark. And why is this diagram and the experiment video looks different? And the answer is we inserted the spaghetti differently, so we used another way. And the second question is the critical curvature, any force or even no will cause the spaghetti into break. I said yes, because we use tracker to check and make sure the velocity is zero and at the next moment the spaghetti will break into barriers. And the third, because I don't have time to answer that, the 8.16 8.76 millimeter is the critical point that it will break. It's about the determinant of the tube. And what will cause the spaghetti to break? And my answer is there is force to cause the break of spaghetti. And the final question is, will rotate during the ejection? I said yes, because it is not the focus of our report. We focus on the high speed and the ejection moment. And when the spaghetti bend, it will store potential energy, and when it gets to the critical curvature, it will break, and part will transfer into an electric energy and the force to spaghetti to inject, while some will release and cause heat. So, right.
You finished?
Thank you.
Thank you very much. Okay. So we invite the reporter, opponent, and the reviewers on stage. Okay. Questions? Any questions for three of them? Yes, please.
I saw a picture of the debris, right? It's fragments. Are the sizes the same, or is a distribution? We talk about the critical bending, right? But I mean the size of the debris. Are they all of the same size?
Yes. One more time.
The debris will fly off at high speed, right? My question is the size of the debris, right? Are they more or less the same, or how different the debris? You have a photo of
Degree means centimeter.
Yeah.
Millimeter.
Oh, they are different. No, these are diameter of the spaghetti, right?
Yes.
I mean the length.
But then, the tube depth, there is the tube depth, and here is the spaghetti depth.
Okay. So here's the.
So that's, I think the title of the last column is wrong. Should be ejected length. I mean, the average diameter shouldn't be 15.34.
Yes, it's average.
That's average diameter.
Yes.
That's the diameter of the length.
The spaghetti.
The length or the diameter?
Spaghetti is
Depth.
length. Okay.
Yes,
That's
diameter.
Diameter is right.
There are two people. The upper one is average length,
Yes.
and the second one.
The second one you say average D.
You said this one and this one.
They both should be the same, right?
Yes, it's the experiment data and this one.
Your D is over here. The distance from endpoint to the point.
We compare the experiment data and the actual data over here.
No, your D is down here. D is the distance from the endpoint of the point of the lunar radius of coverage.
It's right. It's this.
Oh yeah, that's a D. Okay.
Yes.
Any more questions for the three of them?
Maybe I ask. Okay, this is a question for all three of you. The statement says the debris may be ejected. Right? So that statement says, so what are the what's the critical point that there will be no debris? Right? You talk about the curvature, right? So there must be an angle it will not break.
So yes, but the experiment I did is about the diameter of the tube.
Okay, not the bending.
Yes, not the bending.
Okay. So what do you think?
So as the reporter said in the concluding remarks, they mentioned that 8.76 millimeter is a critical diameter of the tube to let the spaghetti not break at any given length, any given D. And so, but this is only when the theta angle between the two tubes are 140 meters. So I think that angle might be a very important thing that we can discuss later on.
I think because when the diameter of the tube change, then the stress will also change. So it will cause the spaghetti to break.
Okay.
I'm a little bit wondering, how do you count the curvature on the outer tube? Because in this diagram, it's contact with the inner tube. And also in the video, it's also contact with the inner tube. But you mentioned that your experiment is using the outer tube.
No, inner tube.
Inner tube.
Yes.
So not that one.
No, not that one. That is the same.
Okay, thank you.
So, no more questions? Okay, thank you. Please take the seat.
Yes, no.
Ready? Okay. For the reporter, 6, 7, 6, 7, and 7. Okay. For the outcome, 8, 6, 8, 9, 8. So for the reviewer, 8, 6, 8, 9, 7. Okay, thank you so much. 好。
刚才你们讲完老师已经讲了很多 comment， 你们可不可以讲一下你们的想法？可以吗？
结果我们最后
可以吗？你们从我不能开始。
好，那蒋老师的想法是说，反正大家已经都。